Well, hello, everybody, and welcome again to yet another OpenShift Commons briefing. And today I'm really pleased to have Redis Labs with us to talk about a long title, Running Geo-Distributed Applications with Redis Enterprise on Red Hat OpenShift. And, lots of good reasons to use the Redis Labs offerings, but one of the things we'll touch on is some of the operators and the workaround operators that they've done. But I'm going to let Cheryl and Madhu introduce themselves, and we're going to get started. The way this all works is if you have questions, ask them in the chat. We'll have live Q&A at the end, and we'll just take it from there. So, Cheryl.
Great. Good morning and welcome. So I'm the Director of Partner Marketing at Redis Labs, and I'm joined by Madhu Murthy, who's a Solutions Architect at Redis. And today, Madhu and I are excited to speak with you guys about running geo-distributed apps on Redis Enterprise and OpenShift. So to kick things off, I'm going to give a brief introduction to Redis and Redis Enterprise, and then Madhu is going to walk you through some of the challenges of geo-distributed apps and how Redis Enterprise and OpenShift can be used together to more easily deploy and manage them. And then we will end with a live demo. So there are two important offerings that we invest in at Redis Labs. One is our open source offering, and the other is Redis Enterprise. And we are the commercial provider and home of open source Redis, and we align very closely with the founder, Salvatore Sanfilippo, his vision, and where we want to go in the future. We also sponsor the open source community, so there's a lot of knowledge that is shared. So for those that don't know, Redis is an in-memory database, and it frequently starts out as a cache, meaning a place to store results of previous queries and interim computations, while the primary data storage is a SQL or NoSQL disk-based database. And Redis has several built-in mechanisms which make it a great choice for addressing common caching requirements and distributed caches. We also offer Redis Enterprise, which provides additional capabilities on top of open source Redis, including high availability, multi-tenancy, and scale, and some really great performance that allows our customers to run on reduced infrastructure footprint. And we have about 8,200 some Redis Enterprise customers, and this continues to grow on a daily basis. Data persistence and high availability in Redis Enterprise really set it apart from the common cache, and we find that customers frequently use Redis to store high velocity data that isn't stored anywhere else. So Redis has been growing in popularity and leadership. And really was the first database container on the Docker Hub to reach 1 billion downloads. And just yesterday, very excited, we learned that Redis was voted the most loved database for a third year in a row from Stack Overflow. So the top three reasons why Redis is incredibly popular is performance, because Redis really makes applications respond faster. It runs in memory with sub-millisecond latency at any load. It's also very simple to use. It offers a variety of scalable ways to use resources, and so it offers more than just simple data structures like a key value store. And because of this, Redis is able to enable faster computation on this data in memory. It also offers extensibility. You can truly take Redis in any direction you want for your application with Redis modules, which include search, graph, machine learning, and AI. Redis can be used to power a variety of solutions, and it has all the capabilities that you need to build modern applications. So just thought we would take a look at a couple of those. Let's take e-commerce for an example. For e-commerce, you need to build a few things like shopping carts, catalog, you need fast search and rendering, and your customers need a low latency payment processing experience and order fulfillment. Redis has all the capabilities required to help you do this with fast searches, quick caching, high-speed transactions, and so on. And we have many customers in this space, including Home Depot, Dick's Sporting Goods, Staples, Walmart, etc. Personalization is another great example. For personalization, you need a really great recommendation engine. And to do this, you need to model behavior quickly and provide recommendations instantly. Redis provides the fast data ingest, the caching layer, and a powerful store for real-time analytics that support these types of solutions. We also have customers using Redis for all these other items that you see here. It's frequently used as a session store, for queue management, time series, and geospatial data. Redis Enterprise is growing fast. These are some of our customers. We are in the top 6 of the top 10 of the top Fortune 500, the top 10 of the Fortune 500, and you'll see that we're in e-commerce, all the different verticals, but we do have a lot of customers in the banking and financial services industry that use us. And now I want to turn this over to Madhu, who's going to cover the architecture of the OpenShift integration and deep dive into some of the challenges and how Redis Enterprise and OpenShift can be used together to deploy and manage Redis applications. And he'll also go into a live demo. So I'm going to go ahead and stop sharing and turn this over to you, Madhu.
Thank you, Cheryl. Let me just go ahead. Cheryl, you can see my screen, correct?
Yes.
Okay. So let's get started before I get into the geo-duplicated databases and how it works in an OpenShift environment. I just want to quickly touch base on what are the functionalities, what are the differentiators between, I shouldn't say differentiators, but the roles that OpenShift plays and what the role that Enterprise Redis plays in an OpenShift environment, right? So Kubernetes is an excellent orchestration tool, and we all know that, but there are certain nuances that Enterprise Redis has that Kubernetes in general finds it hard to handle. This could be a shard failover or a database configuration or monitoring the metrics of the database itself, or when does it need to scale? When do I need to increase a shard from 1 to 2? How do I monitor that aspect? So those are some specific things that are very specific to Enterprise Redis itself. And the other part to that is Kubernetes sits outside of the Enterprise Redis deployment. So it can do a great job handling node failures, node auto-healing, if you will, but it may not have insight into what Redis is doing. So to counter this, to overcome these issues, what we have done at RedisLabs is design a layered architecture where Kubernetes and OpenShift handles anything that relates to the node, like node auto-healing, node scaling aspects. And at the Redis deployment level, at the Redis level, or the Redis layer, we handle anything that relates to Redis itself. It could be high availability. It could be scalability. It could be monitoring. It could be configuration changes. And there are a couple of things that are shared between Kubernetes and Redis itself. And then that could be service discovery or upgrades of the nodes themselves. So having said that, the second aspect is the deployment. How do we actually deploy a Enterprise Redis in an OpenShift environment? So as we briefly discussed, OpenShift is an excellent platform to deploy Enterprise Redis, especially when you talk about automation, especially when you talk about security and scalability from a node standpoint, having a Redis deployment standpoint. So in this particular case, we take advantage of the operator or the service broker, which I'll talk about in the next slide. You can very quickly deploy an Enterprise Redis in 5 minutes and have it up and running in your OpenShift environment. And because of the node affinity, you will need a minimum of 3 nodes, and a pod is deployed on each one of these nodes. And on the right side, you will actually see these are the different components of Enterprise Redis. So you have an enterprise layer that is encompassed by the zero latency proxy, the cluster manager, the REST API, and these are the components that are actively looking at any configuration changes, that actively responding to failure events within Redis. It may be a shard failure, actively responding to monitoring events. So, and then you have the open source layer that is standard open source Redis itself. Now, for further information about any of these, we'll be happy to talk to you, right? I'm not going to dive into the specifics of each of these components on this call. So the different integration options we have the Redis Enterprise operator that is standardized across the board for us. As you know, it helps you maintain a unified deployment across multiple environments. So you may be on Kubernetes migrating to OpenShift, the same deployment would work. You may have multiple OpenShift environments. The operator would continue to work. Operator will will be responsible for anything to do with Enterprise Redis. There is also a service broker aspect, wherein you have a Redis Enterprise in the service catalog that you can take advantage of in providing services to the different businesses, if you will. You could have a small database, you could have a medium-sized database. You can also deploy geo-duplicated databases using the service broker. So now that's the very high-level overview of how it integrates with OpenShift and what are the different components within OpenShift. Let's talk about geo-duplicated applications. So Redis Enterprise offers different replication techniques, right? So you have an active-passive, you have active read replica, and an active-active. So let's just take a couple of minutes, and I'm going to talk about active-passive. Active-passive replication is more like a function that you could use when you have a single source of truth, wherein you have all the writes going to a specific location. As you could see on the screen, I have all the writes going to North America, and these writes would get replicated across the board, across different geographical regions. It could be the West region of the US, it could be Europe, it could be America, South America, it could be the APAC region, any of these. The idea here is, it's all in-memory replication. The idea here is to provide this data locally for applications so that they don't have to traverse the network. A couple of other reasons may be providing this data for analytics purposes in an offline manner, right? So that's where you would use a replica of configuration or a active-passive configuration. The other one is active-active. That's why we're here. So before I get into how this works with Enterprise Redis, I want to take a look at a couple of issues that active-active has. But in general, this is how you would deploy. The idea behind an active-active deployment is you would have two locations that would be serving data for local applications, and behind the scenes, they would be able to synchronize the data in a strong, eventual, consistent manner. So let's look at some of the use cases for an active-active deployment. So these are some of the most frequent use cases that we see with our customers. So the number one use case is managing session data across multiple regions. So the use case could be that you would have users logging into data center A, or maybe the East Coast region, and this morning, and they may actually end up flying to the West Coast, and wherein they have to log in again. You need to make sure that the session data or session state for that particular user is available. Or maybe they're on the plane still logging in, so they're switching from one IP to another IP. So another reason why you would want to have an active environment to facilitate a pretty good user experience. Another use case could be handling cluster failures, right? You could have a complete regional outage. You could have a data center outage, and you want to be in a position where you can take these customers and reroute or redirect these customers to a different location where the data is already available. Another use case could be high volume load distribution across multiple geographical regions. So think about a use case where it's a financial customer and a user has a portfolio. He has invested in a lot of different regions. It could be Europe, it could be Americas, it could be APAC. And there's a stock ticker on his website or on his login page. As soon as they log in, they want to be able to see how the stock market is behaving for those specific ticker symbols across the globe. So ideally, I don't want my application to be traversing the network to go get the latest stock update from each of these regions. So what I would end up doing is define an active-active replication, capture the local stock information and replicate it across the globe so that the data is available locally in the United States. Another example would be in the travel industry. If you're trying to reserve a seat, and make reservations, you want to be able to communicate immediately in an immediate fashion across multiple data centers as opposed to traversing the network. So these are some of the use cases that we have been seeing where active-active is required. So what are the problems of handling active-active? The two major problems, right, that you need to look at. One is the latency aspect. How long does it take for me to replicate this data? That includes, outside of the network latency, you could have a good pipe between two data centers or a decent pipe between data centers. And the other aspect is conflict resolution. How do I handle situations where two applications in two different locations are updating the same piece of data? So let's take a quick look at history, right? So typically, there are two ways you can, considering the different requirements for the modern day applications, this is absolutely important to keep the latencies down. So if you look at the consistency issue or data consistency, traditionally, applications have had either a strong consistency or an eventual consistency. So if you look at the strong consistency, most of the applications or most of the relational models, maybe from 30, 40 years ago, have stuck to a methodology or a principle of a two-phase commit, wherein an application makes an update to the database will propagate the change, wait for an acknowledgement to come back from other nodes, and then send a commit, wait for an acknowledgement to come back. This works strongly in favor of applications that require an immediate strong consistency. However, it comes with a few problems. One is the latency issue. The larger the deployment you have, if you have 7, 8, 9 different data centers, the longer it's going to take to get a confirmation back before you can make the data available for usage. So while that is happening, you cannot use the data. The second important thing is in case there's any network disruptions, because you haven't gotten a confirmation back, maybe the data will not be available till the network issue is fixed. So that is another issue where you would have the data unavailable immediately. So what have the NoSQL market done? So NoSQL markets help evolve this technology, right? So if you look at the likes of Cassandra or Dynamos, they have followed a similar pattern, except that they're not waiting for an acknowledgement. They are following more of a consensus-based quorum. So if the majority of the nodes in the cluster agree that this is the update that they have to go with, they'll end up doing it. So let's assume that you have 7 or 9 nodes in a cluster, and you're propagating a change. One node will try to send that data or propagate that change and get approval from at least 4 or 5 of other nodes. So once that approval is done, the change is committed. The problem still remains. The latency is relatively reduced when compared to a relational model or a two-phase commit. So you could see that it moved from 200 milliseconds to 100 milliseconds. But there is still that is still a very high latency for modern day applications. The second important thing is the data is still unavailable till that quorum is reached. The third more important thing is how does it resolve conflicts? What if in location A, I increase a counter or a score by 10. Location B, I increase the counter by 20. What should be the final value? If A wins this election process or quorum consensus, the final value will be 10. If B wins it, the quorum consensus, the final value will be 20. Effectively, what should be the final value? Should it be 10? Should it be 20? Or should it be 30? Ideally, it should be 30. So that's the other aspect of the problem. How do you resolve conflict? Especially when you have to, if you are going to manage this in an application, what it does is it makes it too hard and too complex to write such code and maintain it and scale it. On top of that, what you also have is Redis offers multitude different kinds of data types. You have the sets, you have the sorted sets, you have lists, you have counters, bit fields, bitmaps. Right, and the idea behind that is it provides you a lot of flexibility, and basically you can utilize one of these data types based on your specific use case to optimize performance. Now, I cannot use the same sort of update methodology, especially when I have so many data structures. It may not apply for all of them. And some of the technologies out there is last right win. If I were to do last right win for every technology, then you would end up having a lot of inconsistent data with Redis 2. So what did we do? So we have decided that Redis Labs decided to adopt the conflict-free replicated data types approach, the CRDPs. The CRDPs is a paradigm shift. Now you could see some of the other companies starting to adopt the CRDP technology. This has been in development or research for over 10 years, and it is based on some science and some mathematical principles. And the idea behind this is to make sure the local database is still available for the application. There's no downtime. And secondly, it provides sub-millisecond latency in terms of performance, whether it's read or write for the local applications. And finally, have the ability to make sure that the data merges or converges and is eventually consistent. So Redis, that way we can offer strong eventual consistency. So these are the different data types, and the idea is, I'm not going to get into the details, but the idea is to have a specific resolution methodology for each one of these data types. So if you use strings, there's a certain principles that is applied. If you use set, there's a certain principles that is applied. If you use hash, there's a certain principle that is applied. And it also depends on the operation that you're using for each. Does append get more priority than delete? Or does delete get more priority than append, right? So there are certain principles applied in each one of these data structures, and based on that, the Redis database responds. So how do CRDTs work? It's a very complicated topic. You can go online. I have a couple of links at the end of this presentation I could show you. But to simplify this, there are several examples out there. You have the G counter, PN counter, G set, 2P set, all these different kinds of examples. But effectively, all of these may use one or more of the mathematical principles. You could use the commutative property, you could use the associative property, or you could use idempotency. In Redis, depending on the kind of data structure, you could use one or a combination of these properties. So for example, how Redis applies the commutative and associative property, right? You have three different data centers. You have A, A, B, and C, and at time T1, all three data centers issue an increment for variable K. A is saying K should be 40, B is saying K should be 50, and C is saying incremented by 30. So the net value, if you take some traditional approach, either last right win, if you go by timestamp synchronized, it would be one of those. If it's a merge operation, it could be one of those. Ideally, I want a combination, a cumulative aspect, right? So in this particular case, the cumulative and the associative properties will apply to the increment, the counter itself, and the final value would be 120 and would be available across all the different data centers. Now, example of idempotency, right? So in this particular case, I have three different data centers, A, B, and C at time T1. This application is inserting a bit image or a image of Wonder Woman in a set. This application at data center B is inserting Star Wars. And this application at data center C is inserting Star Wars and Coco. So what should be the final value for this? Do I have to have in a set? And I need to have unique values. This is because these are the movies that are available. So the final value in this particular case would be Wonder Woman, Star Wars, and Coco. I cannot have duplicate data. And that is what is resolved by using the idempotency, right? A union B union C, A comma B comma C union C will still be A comma B comma C. So that is what is being applied in this particular case. So again, going back to this, the idea behind CRDPs as it applies to enterprise Redis is to make sure that all the data types will use a certain mathematical principle depending on the use case. And based on that, it will merge or resolve the conflicts between different data centers. So how do I create a database? Creating a database is extremely simple. This is my deployment, OpenShift deployment across multiple applications. All I need to do, and I'll show this to you in a few minutes, all I need to do is use a very simple command. The cool thing is all of this communication across all of these different clusters is encrypted. That's the part of OpenShift that actually provides security out of the box. And in case you have errors, for whatever reason, the clusters are not able to communicate, then you will see errors when you're trying to create the database. Once it's established, you will have bidirectional replication, and I'll show that to you in a demo. So how does it actually work? So and this is under the hood. This happens really fast, but I'm trying to explain how well it works behind the scenes. So you would have, as an example here, I would have two different clusters. As soon as I create a database on each one of these clusters, there's a syncer. So typically, there's a two-step process that happens. Let's say an application is performing a read operation. The Redis database will respond back with a sub-millisecond latency to the read command. Now, if an application is performing a write operation, the Redis will perform a local write with the same performance as it did with read and respond back to the client. At the same time, this is where the architecture is a little different. At the same time, once it performs the operation on the Redis database, it replicates that data to what we call a syncer. That's what you see. So every database that's been configured for a CRDB as a CRDB will have a syncer. And the syncer in each location will identify with a participating database and a different cluster and sync the data. So there are three things that can be done when they sync the data. One is if it's a new piece of data that has never existed in the other environment, it's going to go ahead and create that new piece of data. There's no conflict, nothing, it just applies it. You did a set x is equal to 10, it's going to apply x is equal to 10. Now, if there is a update to the data, then it's going to update the data. Or if there is a command that says, you want to delete it, and there's no equivalent command at the same time, then it's going to delete it. The third important thing, and this is what matters the most, is how do you resolve conflict? You could have the application, this is the third step. It notices the syncer that the variable has been, or the data type has been updated at the same time. That's when it starts to apply those mathematical principles of CRDB, depending on the data structure and depending on the operation, and come up and resolve the conflict. So to recap real quick, the idea of Redis Labs Active-Active is to provide strong eventual consistency. You could have read and write with local latency, and usually there are sub-millisecond latency. All the databases will eventually converge. And typically, what we see in a healthy environment is about 1 millisecond plus any network latency that you have. The application is not required to handle any conflicts. It is automatically handled behind the scenes. And the development team can develop as if they're actually designing a single app for a single geo. So my demo environment here is basically, I have two clusters, OpenShift clusters, deployed on the East Coast and West Coast. I have one in the Ohio region, the other one is an Oregon region. I have a simple Node.js app that's basically accepting likes for three different dogs, if you will, in each of these locations. And now we'll see how the replication works. I'll show you another example where I could do the whole movie thing that I just described. We could see how quickly it actually replicates. So here's my environment. I have a very simple one master and 3-node cluster and each of these locations. And this is my OpenShift environment. You could go in, take a look at how the Redis Labs is deployed in each of these environments. I can look at this. I can go look at the applications. I can look at the pods. You'll see that there are 3 different pods. There's a service rigger. There's an operator that's deployed. You can monitor all of this. You can also have a service broker. So this is my east. and I also have a similar environment for my West, right? They both are the same. You can actually see I have a Redis Geo already deployed. If I were to, let me just reconnect real quick and start the application. So I'm actually starting an application. This is my Redis database port, and I'm running the Node server, Node.js on 8080 port, and this is the region. This is where this application is running. This is Ohio. So I have this running, and I can do the same thing. I'm going to do the same thing on the West Coast. And I'm running this in Oregon, right? So let's take a quick look at how it looks like, right? And here, so let's refresh. I have Oregon here up, and I have Ohio up, and these are the different images. So you have a group. The premise here is you have a group of users who are interested in, and you're trying to track what kind of users like what kind of dogs in Oregon, maybe the West Coast, and what kind of people or a section of group would like a fluffy dog, or you're trying to gather some analytics. Now, on the other hand, I also have the Enterprise Redis console, right? I can log into the console. This is how the Enterprise Redis console looks like. You have an entire configuration information here. You can look at how the cluster is performing, all the different metrics for the cluster. You have the different nodes, right? All the different pods that are actually configured for this particular cluster, node 1, node 2, and node 3, and have how many shards are deployed across these nodes, the memory configuration, the persistent configuration. The more important thing is the databases. I can have a single database, or it gives with multiple shards, or as in the case of my East, I can have multiple databases. So it offers a multi-tenant environment wherein you can have multiple databases and you can provide for different applications. Some may be localized, some may be ephemeral that don't require geo-duplication. Sorry, I had to reconnect. So what I'm going to do is quickly start the application again. Okay. All of them have been disconnected. So here's how the deployment looks like. So you have the different pods here. You have the service rigger, you have the operator. I have a UI access. This is going on 8443 HTTPS. Then this is out to the console that I was talking about. And this is the Redis Geo. This is the database that's local. There's a headless service for the database that you create. The operator creates a headless service so that it can manage the database. And I created ingress in this particular case to be able to have access for my application that's external to OpenShift. If you have a Node.js application or any other application deployed within OpenShift, this should be straightforward. You wouldn't need a load balancer if that's what you do. Similarly, I have the same thing on the East Coast, if you will. On the West Coast, sorry, I'm on the West Coast. So, let me just quickly jump back to the Enterprise console. So you can have multiple databases catering to multiple deployments, right? You could have a geo-duplicated database. If you have an ephemeral Redis database, that can be also deployed in your console, in your environment. So it's a multi-tenant environment, each database supporting multiple shards based on your requirement, all within a given OpenShift cluster. These are the different metrics. And the way I would actually create the database is very simple. And so I would go into one of the nodes and execute a simple command, and I can have as many databases as I want. So in this particular case, it's a CRDB create command, and I'm naming what the database name is. So it is geo, memory size. Do I want encryption enabled? The answer is yes. This is the communication between the two clusters, and then it's all going on 443, which is what you would have between two different clusters. This is the FQDN, fully qualified domain name for the cluster, and I also provide the replication TLS SNI on both sides. So once I have that, this is the database I would actually have. That is the Redis Geo database. Now, let's go ahead and just log into Redis CLI. And here's what I have. And let's also log into Redis CLI. So this is the Redis, I'm connecting internal, so I'm just going to use the name of the database. I don't need a fully qualified domain name and the port that it's running on. So let's go back and perform some updates here in terms of how the dogs are responding. So let's assume that I have, okay, before I do that, if I did a key star, I have an empty database on both sides, right? And I just started an application, both of them are running, and I'm not doing anything. I haven't inserted data or anything like that. So let's assume that I have folks from Oregon that actually like a fluffy dog. So I start to increment the counter. You can actually see this data is getting replicated to the East Coast right away. When we talk about a millisecond, that's what we're talking about. And I have folks, and let's take a quick look how it looks like on the East Coast, right? This is my deployment for the East Coast. If I did a key star, you will actually see count 3. And if I did get count 3, you'll actually see the count 3. So that's what actually happened. Now let's assume that the East Coast is doing something like this, and they actually like dogs playing in snow. So I can go ahead and increment. You can see the West Coast changing. So if I were to do both of them at the same time, you will have a counter where it would do a merge of both of these counters and have a net value. So here, key star, and there you go. I have count 2, I get count 2, and you can actually see it's 13. Let's also take an example of sets, right? We talked about a set or a set where I can store these films or movies. So let's say I'm doing Coco. Let's go back here and do S members defined movies. I have Coco. It's already replicated, no problem. Now let's see if I did the same action in both locations, it would be similar to what I'm trying to simulate, adding another same value to the movie's data type or to the movie's key. So if I added Coco again, I get the response back as 0. This means that the value already exists and the command did not succeed because the value already exists and is returning a 0 as a failed thing. So if I were to do S members movies, all you would see is a Coco there. There won't be 2 entries, there's just one unique value. So it did a union, made sure that it did not duplicate the data. So that in a nutshell is how the replication works. And to quickly finish this off, some of the use cases that you want to think about is counters, user activity tracker, session store, distributed caching. You're talking about inventory management, disaster recovery. But please note that CRDB may not be applicable to all the use cases. There are some edge financial use cases where you may still need strong consistency, right? You want to make sure if there are specific financial transactions where you're debiting money or crediting money, may require strong consistency across data centers. So may not be the right CRDB or CRDTs may not be the right fit. And the same thing with order processing. Let's say you actually just executed a card payment and then you lose the connection and maybe it's not replicated or the session did not get replicated. So there is that edge case where you may want to be careful about. So some of these are here. You could go ahead and try the Redis Enterprise. It's already available on Redis Labs. You could go to redislabs.com. There's a lot of documentation there, and we are more than willing to have a quick conversation and show you or get into the depths of the architecture itself. Being a webinar, I could do only a little bit. And then you have Red Hat Container Catalog, the URL is here, and the operator itself is available on operatorhub.io. Questions? Before I answer any questions, these are some of the links. You can go and research a little bit more on CRDT and what strong eventual consistency means. There is one other aspect. I would like to leave you with that part and then cover that. There's something called casual consistency. The idea there is that you want to commit or you want to make the changes in the sequence it has been received, regardless of which location. So, and propagate the changes in the same manner. Let's say in data center A, I have a change happening. A is equal to B, A is equal to 1, then A is equal to 4, and then A is equal to 7. I want to propagate the change in that same manner, affect that change. So I want 1 to be sent first, 4 to be sent first, second, and 7 to be. So that's what we call as casual consistency. Redis Labs with the CRDBs also helps with casual consistency. So I can take questions. That's all I have to cover. Any questions? More than welcome. If not, I'll turn this back to Cheryl.
So there is one more question, at least one more question so far. Matt's asking, does the Redis operator require any external management services? Any plans for an official open source Redis operator? So on the couple slides back, if you could pop over to the operator hub Redis Enterprise one, that would, and maybe pop there.
Yeah, just click on operatorhub.io.
And explain. That should pop you, hopefully, over there. You might have to there. So there's the enterprise version of it. And so maybe if you want to answer that question in terms of this is the enterprise version, and if there's an open source version of it that's coming out, and the other part of the question that Matt's asking, does the Redis operator require any external management services?
So from an open source standpoint, that's a good question. I'm not sure. I'll have to check. But what we have in the operator hub is specifically for Redis Enterprise. And as an FYI, the CRDPs and that are available through CRDBs are available only with the Redis Enterprise. If that is something that you're focused on, I would definitely urge you to take a look at Enterprise Redis so that it can. A couple of other things also is some of the architecture things I talked about, right? So you may want to take a look at that. And if you have a simple installation, I'm sure there should be something, or we may come up with something, but we can definitely validate. The second question is external management tools. Nothing is required. I've shown you the UI where you have all the different metrics. You can set up alerting mechanism. And you also have if you really choose to, we also support sidecar deployments with Prometheus and make that data available for you if you're using Prometheus within your environment. Hello?
That's great. So, Diane, are you still with us?
Yep, I just muted myself. So I'm not. Any other questions? Sorry about that. Let's see, Cheryl, if there's anything else you want to add to that?
No. I think Madhu did an excellent job just kind of walking us through that. But yeah, the slide deck will be available, right, Diane? And so any questions, please reach out to us. Make sure that I put our contact information in the follow-up slides as well.
And if you have any feedback on the operator, please let us know, reach out to us, and we'll happily take your feedback and incorporate it into Operator Hub and into the Redis operator as well. So as Cheryl mentioned, and thank you, Madhu, for an excellent overview and pretty in-depth. I'm going to have to watch this a couple of times before I get everything. And we'll be posting this on OpenShift.com's blog, along with all of the links here and any other bits and pieces that they share with me. So thank you very much for today. We totally appreciate it. And we're looking forward to seeing this again, probably in another month at Red Hat Summit and getting demoed there as well. So hope to see you there as well.
Thanks, Diane.
Thank you.